Okay, now let's look at ways of representing data that are scaled at an interval or ratio level of measurement. Frequently, data that are falling at these scales of measurement are represented in similar ways, um, in part because they are oftentimes treated as being continuous in nature as opposed to discrete. So, we're going to focus on this illustration on ways of representing intervally and ratio scaled data that are also assumed to be continuous. Um, just as a refresher, what is an intervally scaled variable? Basically, with these types of variables, values on the variable are ordered from low to high, and also differences between values are assumed to represent equal differences in terms of the characteristic being measured. So this is unlike an ordinal scale where differences in ranks just simply represent relative ordering. With an interval scale variable, uh, differences between adjacent values represent equal differences on the characteristic of interest. Um, the thing about interval variables is that if they incorporate a value of 0 in the scale, the 0 is just another point along the scale. So a 0 does not reflect an absence of a characteristic. Um, whereas with ratio level data, it incorporates the same assumption that differences between values on your variable represent equal differences in terms of the characteristic being measured. But it does actually incorporate an absolute 0 point. So a value of 0 on this scale would represent the absence of a characteristic. So let's look at some raw data, and we're going to treat this variable, support for the death penalty, as being an intervally scaled variable. So participants in this study rated their level of support for the death penalty on a scale from 1 to 7. I do want to note, technically there's disagreement among researchers whether these types of scales should be treated as ordinal or interval. Frequently, survey researchers will treat these types of scales as intervals. So that's what we're essentially going to be doing in this demonstration. So getting back to the notion of assuming interval and ratio level variables as being continuous, um, when you make this assumption, then we invoke the concept of exact limits. And so the basic idea when you're assuming that your data are continuous is that the values on X that you observe in your data are sort of placeholders for an underlying continuity. So in other words, with enough measurement precision, we could get down to some very fine gradations in terms of the values that would be observed on X. And so the values that you observe in your data set are sort of placeholders for values that could fall within certain ranges of values given enough measurement precision. So if we look at our data set right here, we've got values of 1 through 7, and the concept of exact limits represents theoretical ranges where if we had enough measurement precision where we might observe values um, um, falling. So for instance, if we observe a value of 1 in our data set, the theoretical range of values, if we had enough measurement precision, might fall between 0.5 and 1.5. If we observe a value of 2, we might really be observing values falling in a theoretical range between 1.5 and 2.5. If we observe a value of 3 in our data set, we might be observing values that fall between 2.5 and 3.5, all if we had enough measurement precision. So in other words, the values that we might really observe if we had enough precision might be, say, 0.75, 1.032, 1.496. Those values theoretically would fall between 0.5 and 1.5. But we observe in our data a value of 1, and so the 1 is sort of a placeholder for values that could fall within this range. A value of 2, we could theoretically, with enough precision, we might measure values of 1.61, 2.22, 2.49685. Again, the 2 is sort of a placeholder for the values that might fall within this theoretical range right here. So in this particular data set, our values that we're observing on X are basically serving as midpoints of intervals that represent those theoretical ranges. So there's 0.5 to 1.5. The value of 1 is falling in the center, and so we have, in theory, with enough precision and measurement, we might observe values that fall anywhere between the 0.5 and the 1.5. For a value of 2, we theoretically might observe values with enough measurement precision falling between 1.5 and 2.5, and so forth. So the concept of exact limits represents where the intervals are beginning and ending. And as you can see, the upper exact limit for each interval is associated with the lower exact limit of the next interval. So for example, the upper exact limit for the interval with this midpoint of 1 right here is 1.5. That's also the lower exact limit of the next interval with the midpoint of 2. The upper exact limit of that interval of 2.5 touches the lower exact limit of the interval containing 3, and so forth. So you have basically lower exact limits and upper exact limits representing the bounds for each particular interval, and those intervals touch each other. So the value of X, like I said, is a placeholder for any values that theoretically could be observed within a given interval. So in our current context, the value of X is the interval midpoint, where the lower exact limit is 0.5 below the midpoint and 0.5, and the upper exact limit is 0.5 above. So in other words, if I take 1 minus 0.5, I get 0.5. 1 plus 0.5, I get 1.5. 2 minus 0.5, I get 1.5. 2 plus 0.5, I get 2.5, and so forth. Now we can talk about frequency distributions and relative frequency distributions. And basically, when we're referring to the frequencies and relative frequencies, yes, they are associated with each value that we observe in our data set, but they also capture frequencies and relative frequencies within these theoretical ranges here. So assuming that we had enough measurement precision, we would have, say, 3 cases that fall between 0.5 and 1.5. And the relative frequency between those values would be 0.12, or 12% of the sample would fall between those two values. If we have a frequency of 5, which is associated with our observed value in our data of 2, technically the 5 observed values with enough measurement precision would fall between 1.5 and 2.5, or a relative frequency of 0.20, which would capture basically 20% of the sample there. So the long and short of it is that the frequencies and relative frequencies are capturing frequency and relative frequency counts between our lower and upper exact limits for each interval, under the assumption that if we had enough measurement precision, we would observe, those values that would not be exactly on the whole number, but rather, below or above that number. Okay, so now the next concept to look at are the cumulative frequencies and cumulative relative frequencies. So the cumulative frequency in this particular table represents the frequency of observations that fall at or below the upper exact limit for each interval. So the cumulative frequency for this first interval here is 3, and that would mean that 3 cases fall at or below the upper exact limit, which is 1.5. So basically there's the 1.5. So think about it this way, that we have a frequency within the interval of 3. So at the upper exact limit, the cumulative frequency would have to be 3. The cumulative frequency for the next interval is computed by taking these two and adding them together. So we take the 3 that was a cumulative frequency in the preceding interval and add the 5, which is the frequency of this interval, and that would get us a cumulative frequency at 2.5 of 8. Then if we take that 8 and add the frequency from the next interval, which falls between 2.5 and 3.5, we end up with a cumulative frequency at 3.5 of 13. If we take that 13 and add the frequency of the next interval, which is ranging between 3.5 and 4.5, we had a frequency of 6. So 13 plus 6, which would get us 19. So basically, the cumulative frequency distribution is representing the frequency of cases that fall at or below the upper exact limit for each interval. The cumulative relative frequency represents the proportion of cases in the distribution that fall at or below the upper exact limit of a given interval. And so the same relationship that we saw between the frequency and the cumulative frequencies is also the relationship that we see between the relative frequencies and the cumulative relative frequencies. So we're looking at basically each of these values would represent the proportion of the distribution that falls at or below the upper exact limits for within the distribution of these values within the distribution. So we start with the relative frequency in the first interval, which is 0.12, and just move it over here, and that's where we get the 0.12. So basically, the proportion of the distribution that falls at or below a 1.5 is 0.12. Also, if we multiply that by 100%, we would get, that would mean 12% of the distribution falls at or below 1.5. When we look at the cumulative relative frequency for the second interval, ranging between 1.5 and 2.5, it's 0.32, and that's just simply computed by taking the 0.12 from this interval and adding the relative frequency from the next interval, which is the 0.20, and that gets us the 0.32. So if we multiply that by 100%, that would mean that 32% of the distribution falls at or below a 2.5. If we take this cumulative relative frequency and add the relative frequency from the next interval between 2.5 and 3.5, then we end up with a value of 0.52, meaning that basically the proportion of the distribution that falls at or below a 3.5 is 0.52. Multiply that by 100%, we're talking about 52% of the distribution that falls at or below a 3.5. So that process continues on out until we end up with a cumulative relative frequency associated with the upper exact limit from the top interval, which is 7.5. The CRF, or cumulative relative frequency, would be 1. Multiply that by 100%, and this actually should say 100%, not 1%. So at any rate, these values that are falling in this right here are basically percentile ranks. So like I said, this value in the upper one right here, this should actually say 100%, not 1%. And in fact, just to make this less confusing, I've gone ahead and just changed those values. So when you have data that are treated as continuous, we often represent it using a histogram. And basically a histogram is like a bar chart, except the bars actually touch each other. So we have the values of our x variable along the x-axis, and in this case I've got frequency counts for each value that's observed along the y-axis. And so I could just as easily create a histogram using relative frequencies along the y-axis here, and just keep in mind that I could have actually done that as well. So basically with the histogram, like I said, the height of the bars is representing the number of cases observed falling at each of these values on x. The bars are touching and representing the upper and lower exact limits for each of the intervals. Data that are treated as continuous are often represented too using frequency polygons. You can see in this illustration that the points on the line are basically representing the intersection between the midpoints for each of our intervals and the frequency counts, which are listed along the y-axis. And again, we could have just as easily used the relative frequencies, and in that case it would have been a relative frequency polygon as opposed to a frequency polygon. But notice that basically these this figure right here can easily be overlaid over this histogram right here. So sometimes people will provide both in their visual depictions of the data.
Now, in terms of measures of central tendency for interval and ratio level data, keep in mind measures of central tendency, which are also referred to as measures of location, are designed to address the question of where values on your variable tend to center or be located the most. In other words, the aim is to come up with a value that best represents the entire set of data. The measure of central tendency most often utilized for interval and ratio level variables is the mean, which is the arithmetic average. The mean is computed by summing up the values on a variable and dividing by the sample n, or sample size. For example, let's say I have an interval level variable x with the following values: 3, 4, 6, 2, 1, 4, 7. The mean for the distribution would be computed by averaging those values up and then dividing by 7, which is our sample size. And that would get us 3.857. So that would be the mean for that variable. If we go back to our death penalty variable, we would just basically be adding up the values on x, taking into account the frequency with which those values appear in the data set. So we've got 3 ones that appear in the data set. So we're going to take 1 plus 1 plus 1. We have 5 2's that appear in the data set. So then we're going to take 2 plus 2 plus 2 plus 2 plus 2. We have 5 3's that appear in the data set. So we're going to take 3 plus 3 plus 3 plus 3. We had 6 4's and so forth. So we add all those values up and then divide by 25, which is our sample size, and that gets us a mean of 3.44. So that's the average for our distribution, or the average score in our distribution. Oftentimes, when you're reading statistics textbooks, you'll see formulas such as this that are given, and these are just representing convenient shorthands for what operations to carry out when computing a statistic. So if you see an x bar, the x bar is basically reflecting the mean of the scores on x in your distribution. The sum, this symbol right here, this is basically referred to as a summation operator. It's the Greek letter sigma, and basically what you do is you sum up everything that occurs to the right of that operator. So if you see a sigma and then an x in this fashion right here, this is saying sum up the values of x in your data set. So basically, this right here is the same as what we did in this slide right here, where we added up all the values that occurred in our data set. So that's the summing raw scores on x. And then over the n, we're just taking that sum and dividing by n, which is our sample size. We can also find the mode in our distribution. Basically, it's 4, and that's because we had 6 cases that occurred, or we have a frequency of 6, and there are no other observations on x with frequencies that fall either at that level or lower. So basically, we have a unimodal distribution, and the mode would be 4. But obviously, if we have distribution with multiple modes, we would then say we would have a multimodal distribution. Now the median is computed a bit differently from when we're working with ordinal data. So when we're assuming that our data are continuous, this is kind of the formula for finding the median and assuming an interval width of 1. So in this case right here, you see median is equal to lower exact limit. So really what we have to do is find the lower exact limit of the interval that would contain the median. And remember that the median is that point in the distribution that divides our distribution into equal proportions, basically 50% on either side. So we have to find the interval that would contain the median. Right here, we are taking 0.5 and multiplying by n, and that's the same thing that we did when we were computing the median for our ordinal variable earlier. We just multiplied 0.5 times the sample size. So that's this portion right here. Then we're subtracting the cumulative frequency up to but not including the interval that would contain the median, and then we divide. We take the difference between these values here that are computed and divide by the frequency for those frequency of values that fall within the interval that we're looking for with respect to the median. So in this distribution right here, this is just illustrating how the median was computed. So the median for this distribution is going to have to fall within a range of values. You can see that we have 0.52, so 52% of the distribution would fall at or below a value of 3.5, and the 0.32 that we see right here is actually corresponding, yes, to the upper exact limit of this interval, but also the lower exact limit of the next interval. So at the beginning of this interval, our cumulative relative frequency is 0.32. So we know then that 0.5, or the 50th percentile, has to fall between these two values here. So that's basically how we identify this interval as containing the median. So we're just taking the lower exact limit for this interval, which is the 2.5. Here we're just multiplying the 0.5 times 25, which is our sample size. After taking that product, we subtract the 8. 8 is the cumulative frequency up to, but not including the interval that we're working with in terms of the median. And then we take that difference here and divide by 5, which is the frequency of the interval that would contain the median. And so when we do this and add the 2.5 and the value that we compute here, we end up with the median is 3.4 for our sample data. So this is, you'll see in this PowerPoint, this is just me walking back through the steps. So we have to find the interval that would contain the 50th percentile or the median. That's just we have to first, by looking at the cumulative relative frequencies, and then identify where, which interval is going to contain the median. So that's where the 2.5 to 3.5 come into play right here. The CRF at the beginning of the interval at 2.5, which is also the CRF as the upper exact limit of the preceding interval, that's at the 2.5. The 0.52 is at 3.5 for the upper exact limit of this interval. And so that's how we know that this is our interval that would contain the median. Then it's just a matter of substituting the appropriate values into the formula. So the 2.5 goes where the lowest exact limit is specified. 0.5, the cumulative frequency up to but not including the interval is the 8. So that's being substituted in here. You can see I've substituted the 5 for the frequency in terms of the cases that fall within the interval, and then also multiplying the 0.5 times 25. So when we compute everything in the parentheses first and then add it to the 2.5, we end up with a median of the distribution of 3.4. Just keep in mind that the steps used to find the median, which is the 50th percentile, can also be used to find the 25th percentile or the 75th percentile and that sort of thing. The basic way that we would do that is we would have to identify the interval that would contain the percentile of interest and then go through the same process of substituting the cumulative frequencies and the frequencies that we've done before, multiplying the ends by either the 0.25 for the 25th percentile or 0.75 for the 75th. Now, another way of summarizing data that are falling in an interval or ratio level is to look at dispersion, or basically how spread out or how much variation there is in terms of the values for your variable. So measures of dispersion are basically used to index spread or variation of values in your data. So consider this data from our support for death penalty variable. Now, basically, what I've done right here is I've just sort of manipulated things a little bit. So these aren't the exact values that we had previously. But you can see right here that I've ordered the values on X, and I have frequency counts, and you can see zeros in terms of the frequencies for those values here, and then we have sort of a pileup of values at 4 in this distribution. We have 2 3s and 2 5s. So one way to end, and then in this particular distribution right here, we also have a different set of frequencies associated with the values of X. So one index of spread that we oftentimes see with respect to interval and ratio level data is the range. And basically the range is computed by taking the lowest score and subtracting it from the highest score in a distribution. So the range for the data on the left is actually 5 minus 3, which equals 2, because the highest value observed in the data set is 5, and that occurred twice, and the lowest value in the data set was 3, which we observed twice. So we just take the 5 minus 3, because this is a low and high, so subtracting 5 minus 3, which gets us the 2. In this data set here, we've got values of 1 to 7 and frequency counts for all of those values. So the highest value is 7, lowest value is 1. So if we take 7 minus 1, that gets us 6. So based on the range, we would say that there is more spread or variation associated with this distribution than we observe with this distribution. And so here's a histogram of the range over values. Actually, let me just kind of go back and just kind of substituting the correct um, graphs in here. This is the graph of this data right here. So we can see this. And this is a graph of the data here. So you can see, again, the spread in terms of the range. 5 minus 3 is 2. 7 minus 1 is 6. So basically, that's the difference when we're talking about the range. Now, there are two other indices of variation that's commonly referred to when we're talking about interval and ratio level data, and that is the variance and standard deviation. Now, the problem with the range is that it is a function of only two scores in a distribution, that being the high score and the low score. The variance and standard deviation are a function of all the scores in the distribution. So not just two, not just the extremes, but rather all of them. And so they capture how much variation there is in the scores around the mean of your distribution. So as you can see, in this illustration, we have a set of scores on X and their frequencies and for two separate distributions. And so you can see in this distribution, the ranges are exactly the same. It's just 7 minus 1, which gets you 6. 7 minus 1, which gets you 6. But you can see that there's more spread or variation in the scores in this distribution as opposed to this distribution, where you can see that most of the scores are piling up at 4. So visually, you can see the difference. Both of these distributions have the same range, but there's more variation in scores in distribution B as opposed to distribution A. And that's, again, reflecting the fact that, and so basically the variance and standard deviation will pick up on that fact, whereas if you use the range, you would be assuming that both distributions have equal amounts of variation, which would not be accurate. So how do you compute the variance and standard deviation? So what I've done is I've just created a small little data set of 5 values for variable x, whatever that happened to be. So the first step is you have to find the mean of these variables. So basically, our sample mean, as we saw before, is just simply computed by summing up the values on x and dividing by the sample size. So all I've done is just summation operator x. In the numerator here, it's just summing up 1 plus 3 plus 4 plus 6 plus 7. And then we divide that sum by 5, which is our sample size, and that gets us a mean of 4.2. Step 2 is to compute deviation scores, and a deviation score is nothing more than just taking the raw score on x and subtracting the mean from it. And so basically we're just creating sort of a new variable, if you will, that actually has a mean of 0. And so you can tell with the deviation scores, if you take 1 minus 4.2, you get negative 3.2. 3 minus 4.2, you get negative 1.2. 4 minus 4.2, you get negative 0.2. 6 minus 4.2, you get 1.8. 7 minus 4.2, you get 2.8. So you can see basically where a person's score is falling relative to the mean of the original distribution. If you have a positive value, that person is scoring above the mean. A negative value would mean that that person is scoring below the mean. The next step, step 3, is basically to square those deviation scores. And basically, by doing so, essentially, it's like this. If we summed up all the deviation scores, they would actually sum to 0, which would not really be a good index of how much variation there is. So we get around that problem by squaring those deviation scores and then summing them up. So we square the deviation scores that we computed in this step right here. So we're now computing d squared, which is the deviation score, is equal to x minus x bar, and you can see that that's in parentheses with the square. So this is just basically saying take the deviation score and square it, and do that for each case. So that's what you see in this particular column here. The third step is to sum up those deviation scores. So you see the summation operator, and it's saying sum these squared values of, or these squared deviation scores. So we sum them up and we get 22.8. And basically, this is also referred to as the sum of squares. Step 5 is basically divide the sum of the deviation scores, or the sum of squares, by n minus 1. So you can see we have the sum of the deviation scores, which is what we had right here, and dividing it by n minus 1. And that produces the sample variance. And the sample variance is denoted as s squared, or little s squared. So the sample variance for our distribution is 5.7. If we take the square root of the variance, we get the sample standard deviation. So we're just taking the square root of the 5.7, which you see right here, and that gets us 2.387. The deal is that the sample standard deviation is oftentimes reported in research reports and so forth because it's an index of variation in the original raw score units. If you go with the variance, basically the squaring process takes our index of variation out of the original units of measurement, and it's kind of confusing to interpret. So when we take the square root of the variance, we get this standard deviation, and so this is what is commonly reported in research reports. All right, so we've talked about measures of central tendency and measures of dispersion associated with interval and ratio level data. We can also describe the shape of a distribution, and so we want to keep in mind that there's sort of an ideal shape for oftentimes, which is basically referred to as a normal distribution. And a normal distribution basically follows this general shape right here, and it's basically symmetric. And it's bell-shaped, so it looks like a bell, and it's also unimodal. So think about it this way, that the height of the distribution at any given point is representing basically a proportion of the distribution that's falling within a certain region. And so you can see that um, with a normal distribution, at the center would be the mean, also the median and mode. All three of those would actually line up right at the center of the distribution. And what you see is the greatest proportion of scores would fall in that area right here, and you'll see sort of a trailing off in terms of more extreme scores in the distribution, more extreme lower scores and more extreme higher scores in the distribution. So a normal distribution is basically shaped along these lines right here. Now there are two ways that you could describe whether or not the distribution appears normal. There are two dimensions that we refer to. There's skewness and kurtosis. And skewness represents the degree of asymmetry in scores within a distribution. Kurtosis represents the relative peakiness to tailedness of a distribution. So with a normal distribution, you would have no skew. In other words, if I cut sort of or created sort of a line right at the center of this distribution, then you can see that most of the scores are falling right in the center of the distribution, and you have sort of equal proportions of scores that are trailing off in the upper and lower tails. So when we're talking about symmetry, we're talking about our ability, basically what we see on both sides of the middlemost point within the distribution, or basically the medium point within a distribution. So you could think about it this way. If you can remember in grade school, drawing sort of half a face or half of a heart on a sheet of paper, maybe when you're creating a Valentine's, and you wanted to cut out a Valentine, you might fold a sheet of paper in half, draw out half a heart in relation to the fold, then cut out the shape, and then unfold, and then you would have the whole heart. Well, the same principle would apply here. If you basically took a sheet of paper, folded it in half, and drew out this portion of this distribution right here, and then cut out the shape,
then unfolded the sheet of paper, then it would unfold and look like this. So that's what a lack of skew would basically appear like. If we have a negative skew, what that means is that proportionally more scores are falling in the upper tail of the distribution, and you have sort of a trailing off of scores at the lower tail. So there are fewer scores that are falling in the lower extreme, but you have a sort of a piling up of scores in the upper. So this is sort of the negative skew. So if you think about the negative skew falling on this side here, with positive skewed data, most of the scores are piling up on the low end of the values on your variable, and you have sort of a trailing off in terms of the higher values on your variable. So in this case, this would be positive skew here. Skewness can be assessed using histograms to evaluate graphically and using skewness statistics. And so you can ask for these in programs such as SPSS. Skewness is often centered at 0, which indicates 0 skew. Positive values would indicate positive skew. Negative values would indicate negative skew. And just as sort of a rule of thumb, values that are greater than 1 or less than -1 might be considered more indicative of more substantial skew in the data. So you've got really sort of more of a greater departure from normality with your data, at least with respect to the skewness dimension. Kurtosis is consistent with in this case right here, we have distribution A, which is a little hard to follow, but basically if you follow this on up and down, you can see this is basically what would be considered consistent with a normal distribution. Distribution B has negative kurtosis, and basically you can see this shape right here in relation to a normal distribution. So you see that basically you have sort of thinner tails and it looks more flat in terms of the distributional shape. Distribution C has positive kurtosis, so you have sort of thicker tails here, then you have a peak, and then you have thicker tails out here. So that would be a leptokurtic distribution. So basically, you can see then that there's both skew and kurtosis that bear on the issue of whether or not your data are normal in shape. Oftentimes people focus on the skewness dimension because kurtosis can be somewhat tricky to assess, at least visually, but really normality reflects an absence of skew and really a kurtosis that would be 0, reflecting a mesokurtic distribution. So there are kurtosis statistics that can be computed in programs such as SPSS. Values that are positive would indicate that you have positive kurtosis or a leptokurtic distribution. Negative values would indicate negative kurtosis or more platykurtic distributions. So just as a quick refresher, what we've done, we've reviewed measures of central tendency as they relate to variables of different scales of measurement. We talked about the mode being useful for nominal data, median for ordinal data, but we could also refer to the mode as well, and then mean for interval or ratio scale data, but we could also refer to the median and mode. Measures of dispersion basically are used to indicate how much variation or spread there is within scores within a distribution. Common measures of dispersion that are applied to interval and ratio data are the range, variance, and standard deviation. A percentile is the number of value in a distribution where a certain proportion or percentage of the distribution falls at or lies below. And a percentile rank is a percentage of a distribution that falls at or below a given value. So basically a percentile rank and percentile are basically two sides of the same coin. Frequency distributions contain frequency counts of the times of number, or a frequency of times of a number of values for a variable that appears in a data set. Relative frequency distributions contain the proportions of a data set reflected by different values. Cumulative frequencies refer to the number of times a value for a variable falls at or below a given point within a distribution. Cumulative relative frequencies refer to the proportion of a sample that falls at or below a given point within a distribution. Bar graphs are used to plot out the frequencies or relative frequencies associated with nominal or ordinal variables, and histograms are typically used to plot out the frequencies or relative frequencies associated with interval or ratio level variables, which are generally assumed to be continuous. The distributions associated with interval and ratio scaled variables are often described in terms of their normality or level or degree of normality. So we refer to skewness and kurtosis to address those issues. Skewness statistics can be computed to describe the asymmetry of a variable in terms of which helps us to assess normality, and kurtosis can be computed to describe the relative peakiness to the tailedness of a distribution. So that concludes this basic overview on descriptive statistics.